Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to continue our exploration into the standard normal distribution. And I've got one right here. And let's recall a few things about it. First thing is I think I'm going to scoot it over a little bit. Let's just move it. I'm going to move it over. Probably don't need it quite so big. And put it right there. Okay, now a few things. This is the standard normal distribution. And it can be represented with the notation n, 0 for the mean, 1 for the standard deviation. So that's n mu sigma. Okay, and it has that property of having a mean of 0 and a standard deviation of 1. Now, there's something else, and we're going to see why. Now, remember in our last video, what we said that there's all these little tiny rectangles, and we could just started adding up rectangles like crazy. So we started looking at rectangles like this, and they got so small that you remember I zoomed in and I still couldn't even draw them small enough. Well, in calculus, this is a calculus problem. It's not what we're going to do here today. In calculus, you can make those infinitely small, and then you can find the area over any range. And all those calculations have been done for us. Well, what we have here is this. The tick marks here, this is our the tick marks, here's where the mean is. The mean on the standard normal distribution is always right there at 0. And then the horizontal axis is measured in standard deviations. 1 standard deviation from the mean, 2, and 3 standard deviations. Now, when you're less than the mean, they would be negative. So there's -1 standard deviations, -2, -3 standard deviations from the mean. So I'm going to put this over here. This is the number of standard deviations. And actually, let's just call it sigma. This is the number of sigmas from the mean. And we have a name for that. That value is called a z-score. Okay. Now, this calculus stuff. This calculus has done something very helpful for us. So I'm going to erase my little bars here. Now, what the calculus has found for us is something that's called the empirical rule. The empirical rule. And what the empirical rule says is this. It says that 68%, or you could think of it as 0.68 of data is within 1 sigma from the mean, from mu, from mu. And then it continues. It says that if you were to go to 2 standard deviations on either side, that would be 95%, or 0.95 of data is within 2 sigmas from mu. And it goes one more step. It goes all the way out to 3 standard deviations, at which you're looking at 99.7. Oops, that's a funny percent sign. 99.7%, or 0.997 of data is within 3 sigmas from mu. Okay, now there's a few other things that I wanted to take a look at. There's a few other things that we need to take a look at here about the standard normal distribution. Okay, so the mean, mu, is right in the middle. I'm going to make a list. Actually, yeah. But before I can apply the empirical rule, I need a few more properties. We'll call these properties. Of N0, 1. Standard normal distribution. 1. The mean is always right there in the middle. It's always mean of 0, always a standard deviation of 1. Now the next one, so that was the first property. The second property is it's symmetrical. About mu. What does that mean? It means that this dotted line that I have here extending up from the mean, it means that if this was a piece of paper and I could fold that piece of paper right smack dab on the dotted line perfectly, that the left half would look exactly like the right half. So it's symmetrical about that vertical line drawn straight up from the mean. That'll help us with our application of the empirical rule. Okay, the next one. The area shaded, so I guess I should have a 3 in there, huh? 3. The area shaded under the curve, represents percentage or proportion of data, or probability. Okay, and finally, let's see. We have a few more. Oh, here's an interesting thing. So I always find this just mind-boggling. And then the fourth property says is the curve never touches the z-axis. Remember, we said that the number of standard deviations from the mean, those are called z-scores. Okay, so think about that. That little curve gets really close, but it never touches. As a matter of fact, if I could go and I could draw way out here, and maybe I'm going to put these little check marks in to mean that I had to make a break in my graph, and I continued even further out. And then I was to zoom in like I had a magnifying glass, or I could just zoom in like on this app that I've done. And I was to look at the picture, what I would see is this. I would see this. Just something like that. It's getting closer and closer and closer, but it's still not there. Yet, despite never getting there, what we do know, and this again is another calculus problem, but number 5 is the total shaded area under the curve is, under the curve, ooh, I'm running out of space here, under the curve, you know what I'm going to have to do? I'm going to do this. Okay, let's just make it a little smaller. There we go. That'll work. Now we're back in business. The shaded area under the curve is, I can even use a smaller marker now, is 1. Well, that makes sense. If we said that the probability is the shaded area under the curve, then the probability, the total shaded area, has to be 1. So So far, all of that makes sense and is very consistent. And now I think we're ready. We are ready to use the empirical rule to start finding probabilities. So I want to do this. I'm going to begin with, I probably didn't really need to shrink it that far, but I did, let's do this. I'm going to start drawing these pictures. So let's do these in, how about this green color? It's very pretty. So if I want the probability, I'm going to write it this way, the probability that from -1 is less than z is less than 1. So what we're doing is we're taking a z-score. We want the z-scores that are bigger than -1. I'm going to go back to a bigger pen. Bigger than -1 and less than 1. So it's this region right in here. So if I wanted this region right in here, well, the empirical rule tells me that that is 0.68. Okay, let's do another one. Now, let's try this. Let's try that the probability from -2 less than z less than 2. Well, now what that would mean is I'd go from -2 up to +2. Well, if I shade all of that, that means all the stuff that I shaded plus this additional regions, my picture would start to look like this. Well, the empirical rule says that's 0.95. 0.95. Okay. And you could do that one more time between -3 and 3. It's 0.997. Now, let's I'm going to clear this out, but let's try this. What about the probability that z is greater than 0? Okay, so I'm going to erase this, my green stuff, and let's try that. So the probability that z is greater than 0. Well, that would mean I would shade all of this region. Even that past the 3, I would shade all of this. Okay, now here's where we start using the properties of our normal distribution. Because what did we say? We said that the total area, I mean, if I shade everything green, that's 1. But I didn't. I shaded exactly half, starting from the middle and going to the right. And we know that the middle to the right is exactly the same shape and size and area as the shape from the middle to the left. So we can say that the area greater than 0 is 0.5. Okay, what if we change that? What if I asked you for the probability that z is less than 0? Well, then I would be shading all of this region. All of this yellow region. Well, that's exactly, because it's symmetrical about the mean, that's exactly the same space as if I shaded as the green space. So that is also 0.5. Okay, now let's clear out our yellows and our greens, and let's try another one. Let's try the probability that z. Let's try that it's how about z is greater than 0, but it's less than 2. Okay, let's try that. So here's what we get. 0 greater than 0 but less than 2, and this is an orange. So here's 0, here's 2, so it's this region right here. Okay, well, this is a little bit more interesting. It's definitely not a half because I stopped the shading, unlike in the previous two. Oh, but here's what we know about 2 standard deviations. We know that if I had shaded, I'm going to add some yellow to this. We know that if I had shaded all of that orange plus this yellow region, that would be 0.95. But instead, I shaded from the middle, 0, all the way over to 2. I shaded half of that. So that orange area is 0.95 divided by 2, or 0.475. Okay. Let's try one more. Let's try one more. And I think this should probably be done in this pretty cyan color. So let's try a cyan colored problem. Let's try the probability. Try the probability that z is less than -2. Whoa. Now, if you're thinking this one's hard, I'm thinking you're right. There's a couple different ways we could do this. And so you may take different routes to get there. But let's try this. So the -2 is this blue region out here, all the way out to infinity. Wow. Well, there's a couple different ways we could do that. First off, we know that the yellow plus the blue, let's see this. The yellow plus the blue is 0.5, right? So all of this is 0.5. Well, that 0.5 is equal to that little piece that we don't know, x, plus the piece that we just found, the orange part, which is also equal to the yellow part, which is 0.475. So if I take my probability, that little blue region is the 0.5 minus 0.475. So in other words, it's 0.025. Okay, another way you could have done that is this. You could have said, okay, well, the whole curve is 1. So I'm going to give you one more route. The whole curve is 1. And I know that if I look in between those two curves, that's 0.95. Well, if I take, oops, I'm going to write it this way. That's minus, I'm going to write this way. Oh, need some space. Okay, 1 minus 0.95. If I did that, then what would I get? Well, I'd get the little blue region, plus I'd get another colored blue region. I'd get this blue region too. This right-tailed. Well, that's twice as much as I need, so what I would do is then to just get one of those tails instead of both of those tails is I would just divide this by 2. And I would get the same result again because this is 0.05 divided by 2. All right, that's how we use the standard normal distribution and its properties to find the shaded areas, which represent percentages or probabilities. In the shaded areas represent the probabilities of an interval of possible events. I hope that helps. Thanks for watching.